All right, so let's take a look at some other aspects on when you're data modeling, when you're creating all these data models: aggregation, composition, and generalization. So by aggregation, we mean to look at relationships between two records or two data points that are that might or might not have a life dependency. Right? That one has to exist for the other one to exist. Right? Or there might not be a dependency, or there might be. Right? If one exists, then the other one can exist or not. Or if one exists or doesn't exist, then it means that the other one cannot exist either. Right? So let's look at implementing these things. So for instance, here in this case, you might have a car that has several wheels, the engines, and we order an engine. We want to purchase an engine, and if the representation of this is that we're saying that there's an order, and that order might have a reference or a foreign key, right, to the engine. Right? That it says, I have all those well, in this case, it's just one engine. But if I remove the order, then does the record that's associated with the order, does that also disappear? Right? And so, well, it depends how you interpret it, right? And your interpretation might be different from somebody else's interpretation. Like for instance, in my understanding of what it means to leave Facebook, my understanding would be a composition. But if I leave all my information in there, all my videos, all my pictures, all my posts, presumably goes with me, right? It's a composition. I remove myself from Facebook, everything else goes away as well. But Facebook, in its wisdom, says no. It's not a composition. It's an aggregation, right? Where you leave, but we keep everything else stays, right? It's just a very soft reference that is somehow related to you. But even if you don't exist, this lives on. Even when you die, this will outlive you. So depending on whether there is or there isn't a life dependency, right? That one relationship, one record depends on the existence of some other record. You might model it differently. So to implement aggregation, we use these diamonds, right, as an open diamond. To represent that there is no life dependency. If one leaves, it does not cascade to the other. Right? If one is removed, it does not cascade to the other. The somewhat morbid representation is that there is a life dependency. No person, no hand. That if I remove one particular record, then all the other records cannot exist. Without the whole, the parts can't exist either. And now generalization keeps track of being able to create special cases of other things, right? That allows us to create things that are very abstract and then progressively explain things that might be a little more concrete, okay? And like for instance, in this example, you might have a person that keeps track of everything that is common to all persons. All fields that are shared amongst all persons, right? And then you might have other classes that keep track of things that are specific to subclasses, right? So professor and student, they both have your names and ages and date of birth and social security number. That's all fields that are common to students and professors. But professors might have fields that are specific to professors. They might have an office, they might have a tenure, they might have office hours, a whole bunch of other fields that students might not have. Yes? The same thing with students. They might have a GPA, the graduation year, they might have a whole bunch of things that faculty might not have. Make sense? So generalization allows you to keep track of these dependencies. In hierarchical generalization class diagram, you might have multiple levels, right? Very, very abstract, a little more concrete, a little more concrete, a little more concrete, until you have the most concrete classes. You might have all types of employees. An employee being a person, and then employee. Then you might have a salaried employee. You might have a full-time employee. You might have all sorts of employees with all their different idiosyncrasies, right? Now this we haven't seen how to implement generalization, right? There's again, just like you need to reify to implement something that is many-to-many into several one-to-manys, right? Because you cannot, there's no implementation of that in SQL. Same thing here. Generalization doesn't have there is no equivalence of generalization in relational databases. Right? There's no equivalent. So we do need to see how we would reify this and convert this into something we can implement in a relational database. And we'll see in a minute how we could do that. So here's an example. Here's a generalization. We have a person, a professor, and a student. And we have the student having grades and the professor having an office. And so you might have three tables, right, where you have the person having all the fields that they both share. And then professor and student declaring fields that are specific to each one of them. Right? So that's no-brainer. Right? We know that. So how would you go about implementing this? So let's take a look at an example. You have we have a course, right? We have you have a many-to-many, and you have a course also many-to-many students. So a student is registered many courses, and courses has many students registered in there. Faculty has a one-to-many courses. Here we have TAs assigned to many courses, a course having many TAs assigned to it. Also, there's a specialization here saying that TA is a special case of a student. So it is a student, but it has additional fields. So how would you go about that, implementing that? So what we would expect is 4 tables. Right? So let's implement a couple of these. So let's see, for the faculty, right, we would create the faculty, the ID for the primary key, and the office, right, so the varchar, so that's no-brainer. What about the course? Course, again, we have the number being perhaps like the title or the name. So we have the number of the course, and we have the title or the name. And notice that because we are on the weak side of the course, we need a foreign key going out to the faculty. Who's teaching this? Right? So we have that foreign key at the end. Taught by is a foreign key that references the faculty. Yes? What else? We have the student. So the student is all by itself, right? It's just a class. And notice that even though it has a relationship with course, it's a many-to-many. We need to reify that, right? We need to convert that into a reified table. So there's the student. We have the TA. Now the TA, notice that the TA is going to extend, right? It extends, it inherits from student. What does that mean? Well, presumably, if I want to retrieve information about a TA, all of its information is not in the record of TA. Right? I also would need to do what? I would need to retrieve also the information for the information about the student that is a TA. Right? So half of the information is in the TA table, and half of the information is in the student table. I would need to join both of them, right? And so somehow the TA needs to know, well, where's my other half information? So it needs to be some kind of foreign key pointing to the other record, to the student record, saying, hey, the other half of my information lives out there. I need to join both tables to reconstruct the TA. Make sense? Also, if I remove the student record, or if I remove the TA record, somehow they cannot exist without the other. It would make no sense to have a TA record without the accompanying student record. But it is okay to have a student record without the TA record. Make sense? So we would need to enforce that. We would need to enforce that if the student record for this TA is removed, well, the TA record should also be removed. It makes no sense to keep the TA without the student. Because we understand that these are related to one another as a special case. So to do that, right? Not only do we have a primary key that is both a foreign key and a primary key, meaning that I am pointing to the student ID that this TA belongs to, right? And I'm using that also as my primary key. It's a one-to-one relationship, right? The student and the TA is a one-to-one relationship. I only split it, right, to implement the fact that there's a special case. TA is a special case of a student, right? I'm not keeping all the information in the student. I could have done that, and we will see why we would do that instead, right? there's one way of implementing specialization. There's three ways of implementing specialization. And we'll look at all the pros and cons of which one would you go with. But this is the implementation that the DBA would love, right? Where you split into separate tables. This is called the normalized implementation, right? Where you have for each class you would have separate tables. So not only am I using the primary key, so I know that I belong to the same record as the student, but I also reference the student, so I know that we're one-to-one. And also there's a cascade delete, meaning that if there's a delete in my parent, I am removed as well. Okay, that I cannot live without my parent. Notice that the student does not. Notice that the student could exist on its own, right? And it's completely ignorant of the existence of a TA, right? The TA exists knowing the student. And finally, the two many-to-many, right? That went from course to student and from course to TA. We implement them using these two reified tables that were not there in the class diagram. We substituted the many-to-manys with these two mapping tables. We have a reference to the TA, the course, and enforcing the fact that these two have to be unique. We notice that we have a primary key, a compound primary key that takes a TA record and the course ID together, saying that this TA is only assigned to this course, right? It cannot be assigned more than once. Same thing with the register. We say that this student is enrolled in this course and it cannot be enrolled twice, more than once, right? Another example, we have a vehicle maybe parked in the garage. Every garage has an address. Some vehicles are cars and some vehicles are boats. Every vehicle has a unique VIN number, a power rating, horsepower. A vehicle has an owner, has a number of tires, a car has tires, but a boat has propellers, and they may have a name. Okay, so after parsing that, we might come up with something like this, okay, where you have a car and boat being special cases of a vehicle. All the fields that were common are put in a vehicle, and we have that the vehicle might be parked in the garage. And here's the implementation of the SQL that would go along with that. All right, so we have the table, garage, vehicle. So this is the one-to-many implementation there, and then the base class vehicle, the base class vehicle. Then you have two special cases: the car and the boat. They both have a one-to-one relationship with the vehicle. They both reference the vehicle, and they're also primary keys. So there's a one-to-one, cascade. Right? If you remove the vehicle, you'll remove the boat or the car. It makes no sense to have records of the car and the boat without the record for the vehicle. Okay?